We're looking at section 11.1. We're going to explain how the definition of rational exponents follows from the properties of integer exponents, and then allow for a notation for radicals in terms of rational exponents. So remember that a number a is an nth root of a number b if a to the n power is equal to b. So as you know, the square root usually is indicated by that square root symbol, and the cube root by the cube root symbol. So in general, the nth root of a real number is indicated by the symbol with the nth root outside the square root, where n is called the index of the radical and a is the radicand. So note that when a number has more than one real root, the radical sign indicates only the principal or the positive root. So a rational exponent is an exponent that can be expressed as m over n, where m is an integer and n is a natural number. So we can use the definition of a root and properties of equality in exponents to explore how to express roots using rational exponents. So essentially we're taking a root and writing it to a power, trying to figure out what that power is. So we're saying that the square root of a is equal to a to whatever m power that we have. So if we're trying to get a by itself, we can square both sides. So the square root of a squared ends up being just a. So the power of a power property says when you raise a power to another power, you end up multiplying those powers. So a to the m to the 2 power, multiplying those, we get a to the 2m. Well, the definition of the first power makes a to the 1 power. So since the bases are the same, we can set the exponents equal to each other. So 1 is equal to 2m, divide by 2, m is equal to 1/2. So we can rewrite the square root of a to be a to the 1/2 power. Similarly here with the cube root, you can follow the same process. You end up with the cube root of a being equal to a to the 1/3 power. So can we apply the same reasoning for any nth root? Yes. So that means if we're taking any nth root of a, it will be equal to a to the 1 over n power. So for a positive number a, under which conditions on n will there likely be one real nth root or two real nth roots? So if n is odd, we'll get one solution. So for example, if we're taking the cube root of -8, so n in this case would be 3, odd, we get one solution, and that's -2. Whereas if n is even, that's when we get two solutions. So if we're taking, let's say, the square root of 4, so n is +2, we get two solutions of plus or minus 2. For a negative number a, under what conditions will there be no real roots or one real root? So if n is odd, we're still going to have just one solution. So again, odd n means it would be like the cube root of -8. In this case, again, we have one solution, which is -2. Whereas if n is even n, we're going to have no solution. Because if you try to take, let's say, the square root of -4, we can't do that to get a real solution. We get an imaginary solution in that case. So translating between radical expressions and rational exponents. So changing from a square root to a power. You can do it either way. So the numerator, essentially, the numerator tells you to raise something to a power. So if you're taking an exponent to a power and it's a fraction, the numerator tells you to raise to that power. And the denominator tells you to take that root. And you can do it in either order. So let's say, you can take their example here. We've got 4 to the 3/2 power. So there's two different ways you could do it. You could take 4 cubed and then take the square root, or you could take the square root of 4 and then cube it. Either way you do it, you're going to get the same answer. So it's up to you, whichever way makes the most sense based on the numbers that you have. So they worked through a couple of examples for us there. We're going to look through these ones ourselves. So here, we got 81 over 16 to the 3 over 4 power. So that means we will take the fourth root and then cube it, because both of those are perfect fourths. So the fourth root of 81 is 3. The fourth root of 16 is 2. So then you can cube 3 over 2 to get 27 over 8. We got xy to the 5/3. So we're going to take the fifth root and then cube xy, or you could take the fifth root and then cube that as a whole. So rewriting it the other way. So if we've got the cube root of 11 to the 6th power, what's under the square root is going to be your numerator, and then the root is your denominator. So in this case, it's the same thing as 11 to the 6 over 3. 6 over 3 reduces to 2, and then 11 squared is 121. We've got 2x over y to the 5th, and then the cube rooted. So inside the root is your numerator, and then the root itself is your denominator. So that would be 2x over y to the 5/3 power. So we want to write these into more rational expressions. So with this one, I'm going to take the fifth root of the negative 32 over 243 and then square that. I know that both of those are perfect fifths. You can check those on your calculator. I'll probably show you that in the next video. But the fifth root of each of those would be negative 2/3. So then you square that to get 4 over 9. So that's the simplified version there. 3y to the b over c. So there's two ways you could do this. You could take the c root of 3y to the b power, or the c root of 3y, and then raise that to the b power. So here we've got essentially that 0.5. I'm going to rewrite it as 1/2. 9 under the root is going to be your numerator, and then the root is 3. So that simplifies to 1/2 cubed. 1/2 cubed then is 1/8. And a similar idea here, we can rewrite this one two different ways. Sorry, we can't write. This is the long way. Sorry. So the power is going to be the numerator. The root is the denominator. So we'd have st as a quantity to the v over u. So we can use these in some modeling. So we've got area is pi r squared, volume is 4/3 pi r cubed, and then this equation for t, which is time in seconds for a pendulum. These are all examples of power functions. So a power function has the form y equals ax to the b, where a is a real number and b is a rational number. So here they've used a function, and then they're doing a little bit of solving and rewriting of equations based on these power rules. So let's say we've got a function h of m is equal to 241 m to the negative 1 over 4 that models an animal's approximate resting heart rate in terms of beats per minute, given in its mass in kilograms. So part A, it says a common shrew has a mass of only about 0.01 kilograms to the nearest 10. What is the model's estimate for the shrew's resting heart rate? So essentially what we're doing is we're plugging in 0.01 for m in the formula, and then you can use your calculator. So we'll have 241 times 0.01 to the negative 1/4. I think it ends up with 762.19, which is about 760. So this model estimates the shrew's resting heart rate to be about 760 beats per minute. Part B, we're estimating the heart rate for an American elk with a mass of 300 kilograms. So we're going to substitute in 300 for m. When you plug that in, you'll get about 57.91. So that's about 60 beats per minute then for the American elk. When we come back, we'll finish this problem and do some work on our calculator.